so you can see it.
Yes, it's just not in presenters mode yet.
No, I'll put it now in.
Yes.
Perfect,
Okay.
thanks.
And I have 15 minutes to talk, eh?
12 actually, and 3
Well.
minutes for questions. Yeah, sorry.
I'll rush through it.
And we will mute ourselves and also stop video, but once we put on the video, then you know that your time is almost done.
Okay. Yes, so yes, I'm going to talk about advanced biofuel chain in Emilia Romagna. So the context is that we want advanced biofuels in Europe, a target for 3.5% of the 14% target set for biofuels. There are fuels that are based on low ILUC biomass, and they can either result from a productivity increase or by growing crops on abandoned or severely degraded lands. And in our Biofuel project, we focused on the development of the advanced biofuel delivery chains. And we are going to illustrate this for a chain in Emilia Romagna for biomass to Fischer-Tropsch biodiesel. We have two logistical models that we are using. The BioLocal model that works, that's an optimization model to optimize the organization of a chain according to cost and greenhouse gas emissions. And we have a simulation model, logistics, which works on a finer grid and simulates biomass supply chains in flexible positions, enabling comparison of different chains. So the chain setup is as follows. So we have either a chain that starts from the biomass, going to an Empiro fast pyrolysis plant to produce fast pyrolysis oil, and that oil is then transported to the EFG Fischer-Tropsch unit. And then we have the same chain, but then adding a slow pyrolysis plant for drying the biomass. And this slow pyrolysis plant is also positioned where the Empiro fast pyrolysis plant is placed, but it helps to, it produces heat and char, and the heat can be used to dry the biomass. So the total amount of biomass in the first chain is lower because we don't need the slow pyrolysis to dry the biomass. On the other hand, we do not produce biochar in the first, but we do produce it in the second. And the other thing is that very important to remember is that we need 7 Empiro fast pyrolysis plants units to source 1 EFG Fischer-Tropsch plant. So that is the starting point for our analysis. Then we looked at the different types of biomass. There are many types of biomass tested, field trialed in the Biofuel project. And there is a double cropping system, and also we work with residues, and we work with dedicated crops, perennial crops on abandoned marginal lands. So all these are tested, but the core of this example of our assessment is sorghum, which is produced in combination with wheat as after the wheat yield. We produce fiber sorghum as an intermediate crop. And these results, they were tested in the Emilia Romagna region. So they're really specific to the regional circumstances. And there were also tests with harvesting systems. Then we spatialized our biomass, allocating the potentials to really the agricultural fields that are available in the land use parcel information system. So we spatialized at a very detailed level, combining the current usage with the sorghum double cropping system and estimates of the straw yield. So it's very high resolution information, and that of course was upscaled to do the real assessments in the both models. One at 2.5 by 2.5 kilometer grid in the logistics model, and the other one at a larger spatial entity in the biolocal model. Okay, so if you look at the availability of biomass, we already concluded that if we put giant reed and poplar on unused lands, we would never reach enough biomass to source a full, not even a fast pyrolysis plant, and certainly not a Fischer-Tropsch plant, where you need 7 fast pyrolysis plants. The only option to really make sourcing possible in Emilia-Romagna is based on straw. If you have at least 30% straw mobilization, and also on the base of sorghum in a double cropping system, if we're about 10% mobilization, then we can reach what we need. So that was the starting point for our assessment. Then we mapped at a 20% availability possible clusters of biomass supply for fast pyrolysis plants, and from there, so the red dots are the fast pyrolysis plants given the clustered sourcing area, and the green dots are the possible locations for the gasification Fischer-Tropsch installation. And the possible locations, but we still have to decide which one is the best to choose. Which one has the lowest cost and the lowest emissions. So here you see also the distances to the green spots where you have the possible EFG Fischer-Tropsch installations and over the road. So this information goes into the Bioloco model, specifying exactly the distances between the clusters, the pyrolysis plant locations, and the distances to the 4 possible locations of the EFG plants. This goes into Bioloco, and then in an optimization approach, the best clusters that can source the EFG plant are selected. And these are for mobilization of 10% in a chain with slow pyrolysis, fast pyrolysis to EFG. The first one is the best because it has the sum of transport distances is lowest, and the average cost per liter oil, pyrolysis oil delivered at the plant, at the EFG plant gate, is the lowest. And that is also, we selected the one for 10% fast pyrolysis EFG, 20% slow pyrolysis, fast pyrolysis EFG. So these are the 4 options that we assessed. And then we calculated the cost. And then actually the conclusion is that, yes, not surprising, that the 10% fast pyrolysis EFG without slow pyrolysis is performing better, at least up to the EFG plant gate, and that there is not really a large difference between the mobilization levels anymore, because at 10% actually that's the rate at which the sorghum double cropping is sufficient for 1 EFG unit. If you increase the mobilization rate, it will not very much lead to higher efficiency in transport. Some efficiency in transport is reached, but we also see that the cost of transport and up and downloading, so that the real logistical costs are not that influential on the total cost, because the pyrolysis conversion process is really by far the largest, together with the sourcing cost of the biomass. And these are the results per pyrolysis oil per liter. And of course, again, fast pyrolysis without slow pyrolysis has a lower cost efficiency and also a lower greenhouse gas efficiency. But we still have to address the biochar that is produced in the chain, including the slow pyrolysis for drying. That produces biochar, and that part of the biochar can either be used as feedstock, additional feedstock in the gasification, in the syngas production, or used as an additive amendment to capture carbon in the soil. And this part of the chain still needs to be reviewed in the BQ project, and we are still working on that. But we do know how much the cost and the greenhouse gas efficiency differences are, and so what this biochar system should do to increase the efficiency. Okay, so my conclusions are that setting up advanced biofuel chain based on entirely locally sourced biomass in Emilia Romagna is possible, but requires relatively high mobilization rates. For sorghum, the rate should be at 10%. For straw, it should be a mobilization rate of the sustainable removal levels of straw at about 30 to 40%. And when we only look at fallow and abandoned land for sourcing biomass, you can never reach an EFG plant, and so that is not an option in Emilia Romagna. And the advantage of adding slow pyrolysis is related to biochar and what we do with that, and that needs to be further reviewed. But given the high mobilization requirements, the pre-treatment into pyrolysis oil is a good solution because it enables a sourcing with mixed biomass resources. So you could also mix the biomass going to the EFG by producing pyrolysis oil partly from straw and partly from other crops. That's the advantage. While directly going to EFG with biomass mixed sources is not possible. That's an advantage, and you also create security of supply, and it also increases efficiency in gasification process. Yes, and then I want to, my last slide, there's much more information from the BQ project, which will be presented during this whole conference. You've seen this also presenting tomorrow afternoon, and there are more presentations, and they're also related to this work. And this work was only a snapshot of the evaluations we are doing, because we're comparing many more biomass delivery chains in Emilia Romagna, but also in Mecklenburg-Vorpommern and Brandenburg, and also at EU level. This is and these are the presentations that you can see from IASA, from Fulvio, and from Katja Urgmichen on Thursday. Thank you very much for your attention, and I want to acknowledge all the co-authors. This was really joint work, of course.
Thank you so much, Berrien. I was actually about to say after your speech that more will be presented in the BICUL project meeting that we will have tomorrow at 2:30 up to 6 o'clock. So you are all welcome to hear more about it. So many thanks. Floor, I think we don't have any time for questions.
No, I just had a very brief one because I didn't see one in the chat. So I had a very brief one for Berrien. So you mentioned to take into account the local conditions when you look at the availability of biomass and the sustainable removal rates. So do you take into account, for example, soil conditions when you think about removal rates of straw and sorghum?
Yes, yeah, we certainly do. Yeah, for the straw, and Yeah, for the sorghum, yeah, well, the information that we use is based on field trials. They've been tested in existing rotational systems. So yes, of course, we cannot take account of every soil condition in every field that we allocated the biomass to. But I think it is